Good day everyone, this is the presentation of the Week 11 reporters under the Unit 4, the Alexandrian School, Euclid. Our topic is all about Euclid's foundation for geometry, postulates, and common notions. Let's start with the foundation for geometry. So for more than 2,000 years, Euclid has been the honored spokesman of Greek geometry, that most splendid creation of the Greek mind. Since his time, the study of the elements or parts thereof has been essential to a liberal education. Generation after generation, his book was regarded to as the summit and crown of logic, and its study as the best way of developing facility in exact reasoning. Abraham Lincoln, at the age of 40 while still a struggling lawyer, mastered the first 6 books of Euclid, and according to the previous topic, that the first 6 books of Euclid was all about the introduction for geometry. So that was what Abraham Lincoln had mastered solely as a training for his mind. Only within the last 100 years has the elements begun to be supplanted by modern textbooks, which differ from it in logical order, proofs of propositions, and applications. The first pedagogical improvement was by Adrien Marie Legendre. So Adrien Marie Legendre was famous for his book Elements de Geometria. So Elements de Geometria was a rearranged and simplified version of the proposition of Euclid. So his book ran from an initial edition in 1794 to a 12th in 1823. Nevertheless, Euclid's work largely remains the supreme model of book in pure mathematics. Anyone familiar with the intellectual process realizes that the content of the elements could not be the effort of a single individual. And somehow, this statement is true, because the Book of Elements was not authored only by Euclid. There are also earlier mathematicians who have contributed to the book, like Eudoxus, Hippocrates of Chios, Thales, and Theaetetus. Unfortunately, Euclid's achievement has so dimmed our view of those who preceded him that it is not possible to say how far he advanced beyond their preparatory work. Few, if any, of the theorems established in the elements are of his own discovery. Euclid's greatness lies not so much in the contribution of original material as in the consummate skill with which he organized a vast body of independent facts into the definitive treatment of Greek geometry and number theory. The particular choice of axioms, or now known as the common notions, the arrangement of the propositions, and the rigor of demonstration are personally his own. One result follows another in strict logical order, with a minimum of assumptions and very little that is superfluous. So the book has only a little amount of error that the admiration of the people towards his book is beyond limits. That's why Euclid was not referred to by his first name during their times, or instead the writer of the elements, or simply sometimes called the geometer. Euclid was aware that to avoid circularity and provide a starting point, certain facts about the nature of the subject had to be assumed without proof. These assumed statements, from which all others are to be deduced as logical consequences, are called the axioms or postulates. So in the traditional usage, a postulate was viewed as a self-evident truth. The current more skeptical view is that postulates are arbitrary statements formulated abstractly with no appeal to their truth but accepted without further justification as a foundation for reasoning. So, the postulate and the common notions, or the axioms, they are in the sense of the rules of the game from which all deductions may proceed, the foundation on which the whole body of theorems rests. Euclid tried to build the whole edifice of Greek geometrical knowledge, amassed or accumulated since the time of Thales, on 5 postulates of a specifically geometric nature and 5 axioms that were meant to hold for all mathematics. So Euclid then set forth the 10 principles of reasoning on which the proofs in the elements were based, so introducing them in the following way. Postulates. Number 1. A straight line can be drawn from any point to any other point. So for example, if we have here point A and this is point B, we can draw a straight line. Or if we have point here, this is point C, we'll be able to draw a straight line also. And even here. That means that postulate number 1 is a self-evident truth. Number 2, a finite straight line can be produced continuously in a line. So here's our example. We have line A, B. It is said that a finite straight line or a continuous finite straight line can be produced in a line. So our line is line segment AB. Let's try to produce a finite straight line inside this line. So for example, this is point C and this is point D. That makes a finite straight line. That means that line segment CD is a finite straight line that had been produced from line AB. Number 3, a circle may be described with any center and distance. Okay, so for example, if we have point here, let's say this is point A, and let's put a distance. So this is the distance, and that makes it a circle. Let's try to put it in the center. This is A. And according to postulate number 1, a straight line has point. So let's say this is point B. And if this is a point, and the circle has point and distance, that means that it has a circle in here. So, postulate number 3 is a self-evident truth. So the essence of having these two circles here refers to proposition number 1 that states a line segment AB, which is this line segment AB, there is an equilateral triangle having the segment as one of its side. So when we say equilateral triangle, it is a triangle that has the same sides. So if these two circles intersects in here, that makes it a point C, and according to postulate number 1, that you can draw a line from any point, let's try to do it. And also here. So we have an equilateral triangle here. So this is from proposition number 1. Number 4, all right angles are equal to one another. So for example, let's try making a perpendicular line. That means that we have here a 90-degree angle. So all right angles are equal to one another. So for example, if we have a square, and if these are right angles, that means that angle A is equal to angle B and equal to angle C, also equal to angle D. Angle B is equal to angle D, equal to angle C, and angle C is equal to angle D, and angle D is equal to angle A. So they are all equal to one another because they are all right angles. So postulate number 4 is a self-evident truth. Number 5, if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. For example, this is line Q and this is line P. A straight line falling in these lines. This is line R, and this line R is what we call the transversal line. For example, this interior angle is 100 degrees and this one is 65 degrees, while on the outside angle, this is 80 degrees and this is 115 degrees. So these measurements are just an assumption. So it is said here that the interior angles on the same side are less than two right angles. So 100 degrees and 65 degrees are the interior angle. So let's try summing them up. That means that we have 165 degrees that should be less than two right angles. Less than two right angles. Two right angles is 180 degrees, which is true. But here in postulate number 5, there are geometers who said that this is not a self-evident truth because it is not brief, not simple, and not self-evident. Because we assumed things in here in order to prove it. Like we assumed the measurement of these interior angles. So it was said that Euclid was not fully satisfied with his fifth postulate. Next is the common notions. Number 1. Things that are equal to the same thing are also equal to one another. For example, we have line AB. And let's say line segment AB is equal to line segment CD. So this is line segment CD. Let's say that line segment AB is equal to 10 centimeters. And it is said here that things that are equal to one another are the same. So if line segment AB is 10 centimeter, that means that line segment CD is also 10 centimeter. So number 2. If equals are added to equals, the wholes are equal. For example, line segment AB is equal to line segment DE, and line segment BC is equal to line segment EF. And if these two equal lines are added to one another, that would create a whole that are equal. So let's add segment AB and segment BC. That would result to like this. This is A, B, C. And this one, if we add it, we have D, E, F. So the equal segments are added to each other. That creates also an equal whole. Number 3. If equals are subtracted from equals, the remainders are equal. So what we have here are equal lines. So in common notion number 3, if equals are subtracted from equals, the remainders are equal. So line segment AB is equal to line segment BC, and line segment DE is equal to line segment EF. And also, these two are equal and these two are also equal. So they are all equal. So if we subtract one segment from the whole segment, the remainders would still be equal. So for example, we subtract line BC from line AC, and we subtract line DE from line DF. That would result to still the same size of line segment AB and line segment EF. Number 4. Things that coincide with one another are equal to one another. For example, if we have here a rectangle or a square rather, and this is also a square that's in different position, it would not matter of what are their position. As long as this one square would fit to this another square, they are still equal to one another. Another example is this triangle. It won't matter what are their position. As long as this one, if it would be flipped and it would fit in here, they are still equal. And last, the whole is greater than the part. Okay, so for example, you buy a one whole pizza. We slice it into parts. And if we take this one part of the pizza, so we have this. Even if we take one part of the pizza, still the whole is greater. Still, the whole is greater than the pizza that we take. So that is all for the Euclid's Foundation for Geometry, Postulates, and Common Notions.